Okay, so we're on problem 3, and yeah, I like this question. It's a good way to make sure you really understand the concept of how they define um, a derivative using limits. So before we get to the actual problem, let's back up a little bit and take sort of a more universal case. So let's assume that f of x is differentiable everywhere from negative infinity to infinity. Then the standard in that situation, the standard definition of a derivative is f prime of x equals this limit here. So notice it's h, as h goes to 0, f of x plus h minus f of x over h. Okay, so take an example. Let's say f of x equals x squared, then f prime of x equals 2x. So in this case, we've taken one function and come up with another function. Remember, the derivative, as long as you don't have a specific value for x in mind, the derivative is also a function, f prime of x. So again, the key here is when I say sort of a very standard definition, we don't have any specified value for x, right? We're just trying to find f prime of x for all of x. But once you get to this point, of course, you could say, okay, question, what is f prime of 2? Well, as an example, let's say, yeah, if f of x equals x squared, f prime of 2, you just plug in 2, and of course you get 4. So that's the derivative at a specific value for x. Okay, so that's the prelude. Let's go on to the actual problem. So if you take a look at choice C, I've written it down here, this is just the very standard definition of a derivative, just like on the previous page, and the only difference is they've specified a value for x. It's 2. So x equals 2. And so that being the case, you can plug in the 2 right away as you calculate the limit. So that's what this is, this, and this. So again, I hope I'm not repeating myself, but this is just the standard definition of a derivative using the terminology of limits, but where you've specified a value for x. Okay, so C is a correct answer. Now let's look at some other correct answers. Let's look at A. A, limit as x approaches 2, f of x minus f of 2 over x minus 2. This is an equivalent expression, right? I think you can see, for example, 2 plus h, as h goes to 0, is the same as f of 2 as x goes, f of x as x goes to 2. Same thing. And then x minus 2 as x goes to 2 is the same as h if h goes to 0. So those are truly equivalent expressions. You've just kind of shortened it, simplified it, because, and you can do this simplification only because they've told you where they want you to take the derivative. They want you to take it at 2. Okay, so that's easy. Now, what about D? D is, again, really an equivalent expression to C, except they're just saying, okay, as h approaches 0 from positive numbers. So it's the I forget what the expression is, but it's the limit from the positive side. And of course, that's going to be the same because it's a continuous function and it's differentiable at 2. It doesn't matter whether you take the limit from the positive or the negative side. So taking the limit as h approaches 0 from the plus side is an equivalent exercise. Which brings us back to the standard definition. That's the whole idea. It doesn't matter if h approaches 0 from the positive or the negative side, you'll get the same answer. So that's kind of implicit in this definition. So another way to put it is D is just a special case of C. And then let's look at B. So B, what do? Limit as x approaches 2 of f of 2 minus f of x over 2 minus x. So as you can see, what they've done is they've reversed the sign. They've reversed the sign in the numerator and in the denominator. And it turns out that that's perfectly fine. And the counterexample would be, what if they'd only changed the sign in the numerator so that in the denominator it was still x minus 2? Well, the point here is that, let's go back up to here. This is A. If x approaches 2 from the positive side, then this is going to be a positive number as it approaches the limit, and this is going to be a positive number as it approaches the limit. So the slope, or the derivative, is going to be positive, right? And vice versa, if you happen to approach 2 from the negative side, well, then the numerator would be negative, and the denominator would be negative, and you'd still wind up with a positive value for the derivative itself, the slope. Okay, so the slope is positive, and that makes sense. X squared, if x squared is our function, if x squared is our function, the derivative of f of x, this is f of x, is at 2, let's say f prime at 2 is 4, which is a positive number, which is correct. Okay, so by reversing the sign in the numerator and in the denominator, going back to the original way they've written it, by reversing the sign or the signs in the numerator and denominator, they've guaranteed that it's going to come out the same. So it's an equivalent statement to A. If you want to check that, just imagine that they had only reversed the sign in the numerator. And so this was still x minus 2. Then what would this be as x approaches 2 from the positive side? This would be negative, but this would be positive. And so now you get the wrong sign for the slope. So that's all they've done in B. And then in E, in E, it's just the same concept. They've reversed the sign in the, they've just reversed the sign of h, both in the numerator and the denominator. So it works out to be the same. And so E is equivalent. I don't think I have to go through that. It's the same argument as for B. They just reversed the sign of h. And then finally F. Well, the reason F is incorrect because the denominator is wrong. right? We already know from A tells us that the denominator has to be x minus 2. You can't just suddenly say, okay, let's make the denominator x as in f and say that's an equivalent statement. It's not. To put it another way, the numerator, as x goes to 2, the numerator is going to go towards 0, but the denominator is going to go to 2, and that's just not right. So I hope that all makes sense.